Welcome, everyone. I think we might have a few more people joining us in a few minutes, but it looks like it's pretty close to 12 o'clock right now, so I think we'll go ahead and start. You are in the surface water issues mini breakout session. As in all the other sessions, I'll remind you to have your audio and your video off so that we are not have any extra distractions. Use the chat function during Ariel's presentation to ask questions, put them together. We will have questions at the end of her presentation, so we'll look through the chat session at that point and you can ask questions. I'll go ahead and introduce our speaker now. Our speaker for this session is Ariele Kramer. Ariele is hydrologist with U.S. Geological Survey at the Kansas Water Science Center. She leads multiple cooperative research projects, including sediment monitoring on the Cottonwood and Neosho rivers, long-term water quality monitoring and nutrient and sediment trends in the North Fork Ninnescah River and Cheney Reservoir, and characterization of harmful algal blooms in wetlands and slow-moving rivers above and below Kansas reservoirs. Ariele received a bachelor's degree in physics at Kansas State University and a master's degree in agricultural meteorology from Iowa State University. Looking forward to your presentation, Ariele. Go ahead and begin now.
Yeah, thanks, Lisa. Let me go ahead and share my screen. I think it should be up now. Yes, okay, great. Love to hear that. I have had pretty good luck with getting this shared properly each time, so that's great. Okay, good afternoon, everyone, now that it's past noon. As Lisa said, my name is Ariele Kramer, and I am a hydrologist with the USGS. I'm a project lead for several projects at the Kansas Water Science Center, including the Cheney Reservoir and Watershed project, which I'm presenting on today. My studies cover a range of water quality concerns, from sediment to nutrients to harmful algal blooms, so a little bit of everything. The Cheney Reservoir Watershed study, in cooperation with the City of Wichita, has been ongoing since 1996. And today I will be discussing long-term water quality trends in the North Fork Ninnescah River using EGRET analysis. And all of the information from this presentation is included in a report that was released earlier this year. So I'll have the reference for that at the end. Okay, I think, did my slide transition? Yes, or not? Okay, perfect. Thank you for the nod. Okay, so Cheney Reservoir was constructed in 1965 with the North Fork Ninnescah River as the main tributary. Cheney Reservoir is located just 30 miles west of the City of Wichita. The City of Wichita obtains about, or more than 60% of its water supply from Cheney Reservoir, with the remaining amount from the Equisbeds Aquifer. Land use in the watershed is predominantly rural. All agricultural crops, which are shown in yellow in this figure, including wheat, which is shown in brown, comprise about 55% of the land use. Grassland, which is shown in light green, accounts for about 25%, and 18% of the land use is Conservation Reserve Program land, which is shown in orange. Cheney Reservoir is identified as impaired waters under Section 303D of the Clean Water Act for eutrophication and siltation, with nutrients and sediment being primary pollutants. Taste and odor events in 1990 through 1991 caused the City of Wichita to prompt the establishment of the Cheney Reservoir Task Force. And the task force identified nutrients and sediment as the primary pollutants causing taste and odor issues. Consequently, stream water quality goals for nutrients and sediment were established in an effort to improve water quality conditions for base flow, runoff, and long-term conditions. So far, more than 1,500 contracts have been established for implementation of best management practices in the Cheney Reservoir watershed since 1994. So they've been doing a lot of great work in this area. The North Fork Ninnescah River inflow site is one of our longest running continuous data collection sites in the state. The water quality monitor is suspended from a bridge, which you can kind of see in the background of that lower right-hand picture. It collects hourly water temperature, specific conductance, pH, turbidity, and dissolved oxygen. And then for a period, it also collected nitrate. We have over 230 discrete samples collected at this site, and currently we collect 8 samples per year, and we analyze for all the constituents listed here. So we collect all of this data, so what are we doing with it? Some of the earlier watershed studies focused on identifying sources of nutrients and sediment. But now we have 20 years of continuous water quality data and discrete water quality samples, which is a lot of data, and figuring out how to analyze it in a meaningful way can be challenging. Trend analyses require a long-term data set, and this study was a great candidate for utilizing trend analysis software to summarize water quality trends over the study period. So let's get into some methods, and I kind of apologize in advance. There's some statistical heavy information here, so I'm going to try and cover it and give you as much background as I can to help provide context. But to start, EGRET, or Exploration of Graphics for River Trends, is an R package that was developed to obtain and organize sample data, daily discharge data, and metadata, and show water quality trend information. WRTDS, or weighted regressions on time, discharge, and season, is the method used to explore evolving water quality conditions and easily produce graphs and tables. These methods were applied to the long-term Cheney watershed dataset. And these are just a few of the statistical analysis options and approaches in the EGRET package. There are many more available to users that wish to do trend analysis. One of the more common ways, I guess you could say, to analyze concentrations over time that we've used for this project specifically in the past include linear regression models to compute constituent concentrations. However, common analysis issues include linear regression models being highly related to stream flow and season. There can be also issues with skewed data sets, sometimes issues in added complexity because of censored data, and interannual hydrologic variability can obscure trends or progress in the watershed. So WRTDS attempts to remove some of those roadblocks, but there are data requirements to utilize the WRTDS analysis, which includes more than 100 water quality samples, complete daily discharge record, low intraday variability, meaning the stream or river can't be too flashy. Samples should cover most of the stream flow range, and a 5-year minimum requirement to compute average flux, and a 10-year minimum requirement to estimate trends. If you have a data set that meets those requirements, the WRTDS analysis can help describe watershed changes over time. It's suitable to use with irregularly spaced data. It allows you to estimate concentration and flux, including flow normalized estimates. You can avoid some potential biases and flux estimates from annual hydrologic variability. And you can analyze trends across seasons or flows, since the analysis doesn't assume linear or quadratic forms. So within the Cheney watershed, some of the constituents of interest that have been historically monitored include total suspended solids, suspended sediment concentration, nitrate plus nitrite, orthophosphate, total phosphorus, and total organic carbon. The Cheney Reservoir Task Force identified total suspended solids, nitrate, and total phosphorus as the primary pollutants causing taste and odor issues, and established water quality goals for these constituents specifically. My presentation today will focus on these constituents primarily just for brevity, but the 2021 report includes analysis of all of these constituents and includes summary of continuous water quality data, updates on previously published linear regression models. It provides computed concentrations and fluxes using those linear regression models, and also yields. It also uses EGRET analysis to provide computed concentrations and fluxes, including those flow normalized estimates, and then trend analysis of that data. But I'm also just going to primarily focus on data from the EGRET analysis in this presentation. So the report's kind of massive, but if you're interested in any of those aspects, you can find that entire report online. So why are we interested in flow normalized data? So to break it down as concisely as possible, concentration history allows us to understand impacts on river ecosystem, while flow normalized concentration allows us to better understand the changes in those rivers. And also flux history allows us to understand impact on the downstream water bodies, while the flow normalized flux allows us to better understand progressive changes in the watershed. We were interested in looking at changes in the watershed and the river over the past 20 years, so we focused on the flow normalized concentration and flux to help characterize that. It's important to note that the flow normalized concentrations are not equivalent to sample concentrations, so that direct comparison can't be made. As I discussed earlier, one of the ways we assess water quality over time is using linear regression models to compute constituent concentrations that can't be easily measured in real time. Since both linear regression models and weighted regression models on time, discharge, and season were analyzed in the report, I provided comparison of annual model flux estimates to show the differences between the models. So the WRTDS model computed load is represented in blue, and the linear regression model computed load is in gray in this figure. The relative percent difference between the models ranged from -3 to 25% for all constituents analyzed as part of this study. One characteristic that stood out was the WRTDS model estimates were typically larger during high flow years, for constituents that were modeled using turbidity as a surrogate. These models also tended to have the largest percent difference between the WRTDS and linear regression models. So for instance, in this figure here, the total suspended solids had an RPD of 20%, so it's 20% greater. And then the total phosphorus ended up having an RPD of about 15%. All right, so these WRTDS model output plots include lots of information. So to kind of break it down, the annual mean concentrations included are the small black dots. The flow normalized concentrations are shown as the green solid line. The green dashed line is the 90% confidence interval for the flow normalized concentration. And the thin black reference lines are the Cheney Reservoir Task Force long-term goals. Each dot represents 1 year, and the x-axis spans 1999 through 2019. The flow normalized concentrations allowed us to examine the long-term trends in the concentrations while minimizing the noise from the interannual hydrologic variability that is present when just looking at the annual mean concentrations. It's important to point out that for this analysis, the conclusion about the existence of a trend and the sign of that trend are determined on the basis of the 90% confidence interval. With these confidence intervals, there is widening of the confidence interval around the first few and last few years of the study period, which is expected due to more uncertainty about the underlying relationships near the beginning and end of the analysis period. Because these regressions do not assume a linear relationship, the confidence intervals can diverge to a substantially greater extent than would be seen in linear regression models. There can also be periods during the record when the width of the band becomes larger, which can be indicative that something happened during that period that increased the variability of the estimate, such as a process change or a change in sample density. So now that we have some of the statistical basics out of the way, we can discuss these plots a little bit more. So for total suspended solids, the flow normalized concentrations were smaller than the long-term goal of 100 milligrams per liter. However, the upward trend indicates the goal may be exceeded in the future. Nitrate plus nitrite had interesting characteristics. In the beginning of the analysis period, the flow normalized concentrations exceeded the long-term goal, but continued to decrease to below the long-term goal for the remainder of the study period. There was a noticeable downward trend from 1999 through 2012 when it became relatively stable. And then, however, the 90% confidence intervals do indicate the potential for an upward trend in the future that could exceed the long-term goals. Total phosphorus flow normalized concentrations were greater than the long-term goal for the entire analysis period, including all but one annual mean concentration, in addition to an upward trend. However, there is some indication of leveling off over the last 5 to 10 years. Since 1999, improvements resulting from efforts to decrease total suspended solids and total phosphorus concentrations were not evident from this analysis. Flow normalized fluxes are also important to investigate changes in the watershed. The WRTDS method considers trends in concentrations and flux separately, but does so with a consistent approach for both. This is important because though concentrations and fluxes are closely related, changes in one may be different from changes in the other. So another way to think about it is annual average concentration is a time average of daily concentrations, which means concentrations on days with really high stream flows have the same influence on the average as days with moderate or low stream flow. In contrast, annual average flux is dominated by conditions that happen on the days with the highest stream flow. And the days with the low stream flow are relatively inconsequential to the annual average flux. So it is possible that average concentrations could increase over a period of years, but average flux could decrease if watershed management strategies are helping to reduce non-point source contributions during periods with those highest stream flows. And I see I just got my 5-minute warning, so I'm going to try and get through this. So bear with me. In the case of the Cheney Reservoir Task Force identified pollutants of concern, flow normalized fluxes did not vary substantially over the analysis period. Total suspended solids had a trend probability that was likely in either direction. Nitrate plus nitrite had a likely downward trend probability, and total phosphorus had a likely upward trend probability. Looking at the trends by decade with concentrations in the top half of the table and fluxes in the lower half, you can see the years are broken down by 1999 through 2009 and then 2009 through 2019. And then also the entire analysis period is also listed. The most notable are fluxes for total suspended solids, suspended sediment, and nitrate plus nitrite, which had decreasing trends from 1999 through 2009, and then increasing trends for the second decade, so 2009 through 2019. Overall, although the trend was decreasing, there are indications that the trend has changed in the past decade. The same occurred for nitrate plus nitrite concentrations. Total organic carbon was the only analyzed constituent that showed downward trends over the past decade, though the overall trend was upward. In addition, for this analysis, a lexicon was developed, this not as part of my analysis, but the EGRET analysis, to describe the degree of statistical support that the data set and the associated analysis provides regarding the likelihood that the trend is positive or negative. The descriptive statements were applied to the constituents that I analyzed, and based on the entire analysis period, besides nitrate plus nitrite, all of the constituents had upward trends of some degree for flow normalized concentrations. Suspended sediment and orthophosphate had the highest likelihood of an upward trend, while nitrate plus nitrite actually had a likely downward trend for concentration. Interestingly, even though total suspended solids and suspended sediment concentration had upward trends for flow normalized concentration, there was no evidence of for flow normalized flux. It was likely in either direction. Orthophosphate, total phosphorus, and total organic carbon all had upward trends, and nitrate plus nitrite was the only constituent to have a downward trend. 2 minutes. All right. So in summary, the long-term stream flow and water quality data collection provides a robust and lengthy data set. Analysis showed flow normalized concentrations for total suspended solids and total phosphorus were not decreasing in the North Fork Ninnescah River, and current efforts in the watershed may not be enough to meet the long-term goals that were established. We did also look at some of the TMDLs, and flow normalized trends for sediment flux didn't show an increasing trend, suggesting that the 10% reduction specified may be attainable. And the total phosphorus did exceed the TMDL 14 of the 20 years in the study period. It's still important to consider that effects of best management practices on water quality are highly variable, and linking changes to causal factors requires consistent monitoring before, during, and after changes are made. For this study area, a complete long-term data set of specific BMP types implemented in the watershed and their locations were not available, making interpretation of the trend results, such as causal analysis, more difficult. And we must also consider that detection of the effects of these BMPs may not be possible at the watershed scale unless it has a substantial effect on concentration or transport. I got my 1 minute warning, sorry. And is measured over a long period of time. So if there are only minimal effects on concentrations or fluxes in the system, it's going to be difficult to detect those changes at the watershed scale, regardless of the size of watershed. So it doesn't seem that I'm going to have time for questions. Sorry, there was a lot of information to pack into that time frame, but I did include my contact information. So please feel free to email me if you have any questions that we don't have time for today, or send me a chat in the, I think you can do direct messages too. So thank you. I appreciate the time to present for everyone.